When both eigenvalues are negative, how do we classify the equilibrium point at the origin? Sink, yeah. And when one eigenvalue is positive and one is negative, saddle. And both positive, the origin is a source. Okay, so just to remind you, Monday is somebody's going to come in and administer a survey. It will take anywhere from 15 minutes to 50 minutes. And I will have your quiz ready for you. So as soon as you finish the survey, you can start working on the quiz, and it will be collaborative. And you can take it home after, because I have no idea how long the survey is going to take, and if you'll have enough time to finish the quiz after it. So you can use the remainder of class to work on the quiz together. And then you can take it home and bring it back Wednesday. I'll also have the quiz you handed in Monday back for you on Monday. Okay, so phase portraits for linear systems with real eigenvalues. So today is going to be a lot of review of what we did last class, which is good because there was a lot there. And also we're going to add just a little bit more, like a one step further, and be able to use the straight line solutions that we found to create a phase portrait for the system. And remember, a phase portrait is a picture in the XY plane where we sketch multiple possible solutions, lots of different initial values, so you can get a qualitative idea of what all the different solutions look like. Okay, so here we've got a linear system, and we want to find the eigenvalues by solving the characteristic polynomial, right? So the characteristic polynomial is the determinant of a minus lambda I. We set it equal to 0 and solve for lambda. All right, so I need to do the determinant. And then I put a big square bracket here because I got to do a minus lambda I before I take the determinant. So a is 8, negative 11, 6, negative 9, minus lambda times I, which is the matrix 1, 0, 0, 1. All right, so I'm going to do all of this that's in the big square brackets right now in my head, right? So when you distribute the lambda to every term in this identity matrix, you're going to get lambda 0, 0, lambda. And then when you subtract matrices, you subtract corresponding components. So upper left minus upper left, upper right minus upper right. So this is going to become 8 minus lambda. And then I'm going to have negative 11 minus 0, which is negative 11. And then I have 6 minus 0, which is 6. And negative 9 minus lambda, like that. Any questions on how that calculation is done? I know if you didn't take linear, I sort of like threw matrix arithmetic at you really fast. So let me know if there's questions there. All right, so the idea is now I want to take the determinant of this, and I'm going to set it equal to 0 and solve for lambda. And how do you take the determinant of a 2 by 2 matrix? Close. AD minus BC. Yeah. So it's these two multiplied together minus those two multiplied together. So it's going to be 8 minus lambda times negative 9 minus lambda minus negative 11 times 66 is negative 66. So that becomes plus 66 because it's minus negative. All right, how do you solve this equation? I got to FOIL it out, combine like terms, and this is going to become a quadratic. Yeah. So if I FOIL this out, I get negative 72 minus 8 lambda plus 9 lambda is plus lambda plus lambda squared plus 66 equals 0. So combine my like terms, I have lambda squared plus lambda. 66 minus 72 is negative 6. And then that factors lambda plus 3, lambda minus 2. So we get lambda 1 is going to be negative 3. Lambda 2 is going to be 2. Set each factor to 0. So there are my eigenvalues. And which one you call lambda 1 and which one you call lambda 2 is totally irrelevant. Doesn't matter. Okay, so to compute eigenvectors that are associated with each eigenvalue, there are an infinite number of eigenvectors associated with each eigenvalue. In fact, there's a whole line of them. That is the straight line solution. It's made up of all the eigenvectors. So we just need to find one, and we'll know the entire straight line solution and the analytic solution to the differential equation. All right, so let's, for lambda 1 equal to negative 3, we need to solve AV equals lambda v. And v is a vector. It's written in bold there, so it's actually a vector xy. Right? Because these are my vectors xy's. Usually we call those things y's. That might be confusing. I'm using v for vector. Doesn't matter. All right, so A is the matrix 8, negative 11, 6, negative 9. Times some unknown vector xy has to equal lambda, which is negative 3 times xy. So this is actually a system of equations with two unknowns. This actually says 8x minus 11y has to equal negative 3x. Because when you multiply this matrix times the vector xy, remember you dot product the 8 and the negative 11 with the x and the y, and that should equal the first component on the right-hand side. So that would be negative 3x. So when I solve this thing, you get 11x has to equal 11y, so x has to equal y. In the second equation here, let's just make sure it doesn't tell us something different. We'll just see if there's any more information there. So that says that 6x minus 9y has to equal negative 3y. So 6x has to equal 6y, so x has to equal y. So same information. So whenever you're doing these, it's a classic result is that either both equations give you the same information, or one equation gives you no information at all, and you just use the other one. So if x has to equal y, give me one eigenvector, 1, 1, right? Would be an eigenvector associated with this eigenvalue. So I'll put that up here, 1, 1. Goes with lambda 1 equals negative 3. All right, and then we do the exact same process for my other eigenvalue. Lambda 2 is 2. So I do 8, negative 11, 6, negative 9 times xy is supposed to equal 2 times xy. So 8x minus 11y has to equal 2x. And 6x minus 9y has to equal 2y. So let's see what information these equations give us. This says 6x has to equal 11y. So y is 6/11 times x. Yeah, and then over here, 7y has to equal 6x. 11y, that's good, because I was like, we're getting different information. 11y has to equal 6x, so again, y is 6/11 times x. It's the same, yep, because it would be the same line, and any point on y equals 6/11 x is, it's the same line, yeah. All right, so give me one eigenvector that's on the line y equals 6/11 x. 1 and 6/11. What if I didn't want to deal with fractions? 11, 6. I could make x 11 and then my y would be 6. I'm going to do that. 11, 6 is my eigenvector of choice because I didn't want to have a fraction. So you can pick any x you want. I picked 11. 6/11 times 11 makes y 6. So in the x spot 11, y spot a 6. Okay, so I have eigenvalues and eigenvectors, 2 each, which means that I can write down 2 particular solutions to my system of ODEs. Each particular solution has the form e to the lambda tv, and because I have 2 lambdas with 2 v's, I can write 2 of these down. So y1 is going to be e to the lambda 1, which was negative 3t, times the vector v1, which was 1, 1. And y2 is e to the 2t, my other lambda value, times its eigenvector, which was 11, 6. You can either leave it like that. There's a lot of notational choices that you have to make at this point. And they are choices. There isn't a right or wrong. You could circle that and be done. Or sometimes you might find it clearer or making more sense to you and not necessarily to other people, but you might want to distribute this constant that's out front, the e to the negative 3t. You can multiply it times both components of your vector, e to the negative 3t, e to the negative 3t, and y2, which this is actually a function of t, so you might want to write that. It's a personal choice. And we have 11 e to the 2t and 6 e to the 2t. And you might also just, again, personal preference, remind yourself that's x of t and that's y of t. Right? So that's an x of t and that's a y of t. And maybe I'll put little subscripts to make them go together. So like I said, there's a lot of notational choices. Just do what makes sense to you to like help you keep track of what these things actually are. So you could have stopped right here and just circled this, right? Or maybe you would have done this. All right, so we want to check that the 2 solutions we found are linearly independent, because that's important to be able to combine them in a linear combination to get the general solution. They have to be linearly independent. And it turns out that in general, if you get 2 distinct eigenvalues, 2 different eigenvalues, then they will always produce 2 linearly independent solutions. So after we do this problem right now, I won't make you check it again, but I just want to verify once that they are linearly independent. So I want to do y1 of 0. So let me just re-jot down what y1 of t was. It was e to the negative 3t, e to the negative 3t, right? We can just come back to previous example. E to the negative 3t, e to the negative 3t. All right, so when I plug 0 in there, y1 of 0, put in 0 for the t's, and I'm going to get 1, 1. Then I do the same thing for y2 of t, which was 11 e to the 2t, 6 e to the 2t. Okay. And then if I put in a 0 for t, I get 11, 6. 1, 1, and 11, 6. Are they linearly independent vectors? Yeah, one is not a constant multiple of the other, so they are linearly independent. Okay. So we learned several classes ago that if you have two linearly independent solutions, particular solutions, all you have to do is combine them in this linear way, and you have the general solution to the system. So y, my general solution is going to be y is equal to k1, some unknown constant, times y1. And y1 is e to the negative 3t, e to the negative 3t, plus k2 times y2, and y2 is 11e to the 2t, 6e to the 2t. So there's my general solution. Again, for some people, it might be more comfortable to distribute the k1 and the k2, right? So this would actually be, and then maybe add the two together, right? Distribute the constants and add the vectors component-wise. So my final vector would be k1 e to the negative 3t plus k plus 11k2 e to the 2t. That would be my first component. And then my second component would be k1 e to the negative 3t plus 6k2 e to the 2t. And then it might be helpful to remind yourself this is actually the vector x of t, y of t. Yes. Mm-hmm. What do you mean, wrote all what out? Where are the y's, x's and y's coming from? Are you sure? Yeah, you could pull things out of here. Like you could write k1 e to the negative 3t outside and then have 1, 1 in here. Yeah. You could pull out e to the 2t, so you'd have k2 e to the 2t out of the parentheses and then just have 11, 6 in the parentheses. Like there's lots of ways to write this that are correct. So I've tried when I've been like writing down the answers for you in the back to like sort of alternate the way I do it, so that you can see all the different ways to write it that are correct. All right, so there's my general solution. Again, you could have circled this. You could have circled this. And there's even another way that you could have written it, but I ran out of space. So, all right, so in this vector field, I want to sketch the two straight line solutions that we found. And those are corresponding to the eigenvectors, right? So remember, lambda 1 was negative 3, and it corresponded to the vector 1, 1. And then lambda 2 was 2, and it corresponded to the eigenvector 11, 6. My straight line solutions are the lines that go through the origin and these points. So let's see, I've got 1, 1, or 5, 5, doesn't matter, any eigenvector. It always goes, straight line solutions always go through the origin. So you get one eigenvector and you plot it and then you connect it to the origin. And you can see in the vector field that the arrows are all pointing in a straight line. So this straight line solution corresponds to lambda 1, which is negative 3. So I just like to label it just so I can remember which which one it is, because the lambdas do tell us more information. We just aren't there yet. Yes, and so the arrows of the vector field are all pointing at the origin, right? That's because the lambda value is negative, right? Whenever the lambda value is negative, the solution points at the origin. So I didn't draw these in, I should have. If you're drawing it on a vector field, it's quite clear the direction of the solutions because the vectors are all pointing that way. But if you're just drawing a phase portrait and you don't have all these arrows, you want to make sure you put these in. Because we do know based on the fact that the eigenvalue is negative. Okay, and then my other straight line solution is the line that goes through the vector 11, 6. So maybe I'll do that in a different color. 11, 6 is about right there. Draw that line through the origin. Yeah, there we go. That's a terrible looking line. Whatever. Okay, and then this corresponds to lambda 2, which was 2. And that lambda is positive, which means these guys are pointing away from the origin. Okay, I gotta draw this better. Why does my vector field look so funny? Just like that. There it is. Arrows are pointing away from the origin. All right, so then I want to use the direction field to sketch several other solutions. And once I have several solutions sketched, that is what we call a phase portrait. So if my initial condition were 5, -5, my initial condition, I can follow the arrows and they are leading me towards my straight line solution, right? And the same theory that we talked about, like in chapter 1 with existence and uniqueness, that said you can't cross solutions, the same thing holds when you're dealing with a system that has 2 variables. Should it be curved? Yeah. Yeah, that's not the best. Mm-hmm. Curving away from the line. Yeah, it kind of does. But it, yeah. I don't know, something like that. And then the direction, the arrows are all going like that, in that direction. And then if I chose an initial condition over here, like in the second quadrant, it would do something like this. And again, this is very qualitative, just trying to sort of follow the vectors. And then in between my 2 straight line solutions, I would have something like this, going in that direction. And over here, I've got something like this. And that's a phase portrait. Phase portrait is where you sketch several solutions in the phase plane that correspond to qualitatively different initial conditions. So by qualitatively different, I mean like if I chose another initial condition over here, like this one, it would look very similar to the one I drew right here. Qualitatively, they do the same thing. So you can draw more than one, it's fine, but you don't have to. Okay, so it turns out that this phase portrait is typical whenever you have one negative and one positive eigenvalue. When the solutions around the equilibrium point behave like this, right, where they sort of use the straight line solutions as asymptotes and This picture actually looks kind of like a saddle, right? So we call it the equilibrium point, a saddle. Okay, so one last thing before I let you work on stuff on your own is I want to find the particular solution that satisfies the initial condition 0, -5. So I'm going to sketch it on here. 0, -5 is right here. And so if I try to follow the vector field, it's going to do something like this. Something like that. That's my particular solution. And if I want to find a formula for it, I can go back up to my general solution. And I'm going to plug in my initial conditions and solve for K1 and K2. Okay, so I got my general solution written down here. So y of 0 is 0, 5. So what that means is that x of 0, y of 0 equals 0, 5, right? Because that y is bold, which means it's a vector, which means it's actually an x, y. So x of 0 is 0. So when I plug a 0 into my x coordinate of this vector, I got to get 0. So I'm going to have k1 e to the -3 times 0 plus 11 k2 e to the 2 times 0. That has to be 0. And then my other equation says that k1 e to the -3 times 0 plus 6k2 e to the -3, e to the 2 times 0 has to equal 5. Yeah, -5, thank you. And then I have two equations with two unknowns. I'm going to solve for k1 and k2. So this says that k1 plus 11 k2 is 0. And this says k1 plus 6 k2 is -5. So I have a k1 in both of these equations. I'm going to use elimination. You could do row reduce echelon form if you know how to do that, or you could use this old technique from an early algebra class. So I've got two equations. I can add or subtract them. K1 minus K1 is 0. That goes away. 6K2 minus 11K2 is -5K2 equals -5 minus 0 is -5. So K2 is 1. Then I come back over here. I put in a 1 for K2. So K1 is -11. And then I'm almost done. All I have to do is rewrite the solution, replacing K1 and K2 with the numbers. I don't really want to, but I want to make sure that you know that that's what you have to do. X of t, y of t equals K1, which is -11. Plus 11K2, so plus 11 e to the 2t. And then K1 and 6K2. There we go. And that would be a perfectly great way to write that. Just for practice, I'm going to translate it to a sort of a more compact way of writing it. Y equals, I'll pull out -11 e to the -3t. And then my vector left is 1, 1. And then here I'm going to pull out e to the 2t. And my vector left is 11, 6. just another way of writing the same thing. Okay, so we just explored equilibrium points that can be classified as a saddle together. You have two problems to do where you're going to explore sinks and sources.